Right, the second presenter is Burley. Well, it's Daniel Burley. I call him Dan. Well, I think some other people call him Dan too, but candidate for the Bachelor of Science degree in Electrical Engineering, major GPA of 3.79, cumulative of 3.9. Dan was one of the first students to approach me timidly but quite confidently when I started my career here at ENC in summer 2011. He came to me and said, I want to see who the new prof in town is, you know, something like that.
Father was Indian.
But since then, I've been working closely with Dan on several projects, such as lab rehabilitation also, and internships. So in summer 2012, Dan did the summer internship at Bose, and since then, he has been transformed. Transformed by the experience and transformed by the exposure. Since then, we've witnessed his confidence level increase many folds, and his technical capabilities and dedication to engineering also are very noticeable. So as a result, I gave him a tough senior design project to do. And now he's in a good position for a very promising and lucrative career. And I'll come visit him when he graduates. So the title of his talk is Multipath Interference in RF Transmission Channels. So it's a good pleasure to welcome Daniel Burley to join you for seminar series.
I should probably wear this. Be unnecessary. Hello everyone. As you know, I'm Daniel Burley, and today I'm going to be talking about multipath interference in RF transmission channels. So a brief overview of what we're going to be going over. So we need to talk about what exactly is multipath. Up till now, I've told a few people about what my project is, and everyone's like, what is that? Nobody knows what that is. We're going to talk about how multipath propagates in the air. And then all this stuff here is just a bunch of technical details that all culminate in the problem of multipath. So, what is multipath? Over here you see we have this cell phone here that transmits a signal, a radio frequency. That's an electromagnetic wave that goes out into the air. Now that's transmitted in all directions. And so you see what can happen is we can have one of them head right over there to this building, one heads over to this building, and one heads and hits this building, and they bounce off these buildings, and then they all come together and they reach this receiver here at the same time. Well, when they reach the receiver like that, the waves actually add together and you get a distorted signal. And the phase is all messed up, and you can have all sorts of junk on top of there. So, to get a clearer picture of this, what we can do is we can look at sine waves. Sine waves is there one example of an electromagnetic wave. Oftentimes when we send out waves, they look like this. And so what happens is right up here we have a wave two waves that are perfectly out of phase. So this is out of phase by 180 degrees. And when you add these two phases together, all your signal is gone. You have no signal left. So if you were talking on the phone, they received that, you drop the call. You can't talk to them anymore. Sometimes though, the phase isn't that perfect. Most of the time, it's off by a little bit. So here, we're off by a little bit, and we actually get more signal, but it's still out of phase, so it's still distorted. And these are just other examples here. This one's a larger phase difference, and actually we have less signal, so that both can happen. And then down here, I actually use 3 signals, because oftentimes you don't get 2, you get 3 or 4 or 5 or more. And those add just the same way. On the right here, this is all that stuff that you get from transmitting it in the air. All that, these squiggly lines here, that's the noise that's added into your waves. And when you add them together, you get this crappy signal here. Well, how do we go from this red signal here back to the blue signal here? Because I said over here, oh, the blues are my original signal. I want the blue signal, but I have the red signal. How do we get that? So, we have to talk about how we model these transmission channels. So when we send a radio frequency out, it has to go through a transmission channel, which is the air. We start with a digital string here. So that's a bunch of 1s and 0s. We turn that into a transmittable wave. if we look at this in the frequency domain, this is what it looks like. This is a baseband signal. We can transmit this thing out there. Okay. After we modulate it, this is what it looks like in the frequency domain. So what we want to do is we want to go back to this one after transmission. Right? So we've modulated this thing, and here's where we are right here. And we add our noise, which is all that squiggly lines, and we send it out. So we have to try to go back. How can we go back to this right here? Well, we use demodulation. So we modulated it originally. We have to demodulate it to get back. So what we do, we actually have two different ways we can do this. The first way is just to multiply the signal by the cosine wave that we used to modulate it. And then we just put it through a low-pass filter here, which is what we see down here, and we get this nice peak, which is that original signal. So when we multiply by that cosine wave, we end up with all these things. This is these two things out here. And when you multiply that by each other, you end up with two more and the original one. And then this is all that noise. So by using this low-pass filter, we cut all of that out and end up with this. Another way we can do this is simply by squaring the electromagnetic wave that we get. So we take all this information into the receiver, we end up with this wave function. We can square that. We take the square root of that squared term, and then again apply a low-pass filter. And this is what we end up with. Same thing. But we're not done. The biggest issue is this relay right here. That's our multipath. So the multipath is actually a much nastier kind of distortion than the Gaussian, all the squiggly lines, the Gaussian distribution there. So what we have to do is we start with our original modulated signal, we add in our multipath, and then we add in our Gaussian, send it out, and then we have to demodulate from that, which happens to be a much more difficult problem to do. You also see over here we have this division by Rayleigh. We cheated there because this is actually a really difficult thing to do. That's normal equalization. In order to demodulate this effectively, we have to do equalization, and that's something that we can do, but it's a really, really difficult process to go through that. So instead, we just cheated and used our original wave function, which we already knew. And again, we just add that low-pass filter on here. Now you notice this is actually slightly different. Because I added that multipath in there, I have these additional signals that are sitting on top of my original signal. So that will distort my signal. Even when I take this low-pass filter, they're still in there. So I have my original signal plus all those things on top of it, which distort it. We have to come up with a way now to mathematically express this. So back in the 1940s, this gentleman by the name of Nakagami developed an experiment with which he could gather data and find a mathematical expression for this. So what he did is he set up his experiment. This is a diagram of it up here, and he took lots of pictures, and then he overlaid all those pictures, and this is what he got. Okay, and so he's able to use these pictures to all these data points here to fit a curve to them. Right? So he fit a curve somewhere in here, and he came out with this right here, which is our multipath fading. So he actually developed this M-type distribution because he realized I can just take my equation that I have, and by changing parameters within the equation, I can come up with all these different fading distributions, all these different interference distributions, and those I can use those to model multipath interference, Gaussian noise, and a bunch of other, Ricean, other things like that are in there. So for us, the green line here is the Rayleigh, and the blue line here is actually a half Gaussian. So we're actually using those two here today. Now I wanted to try to take all this stuff I have all set up and ready to do and implement it using an actual signal. Because when you're talking on the phone, you need to, be able to actually do this. So I took a wave file And the first thing I needed to do was turn it into a digital signal. So that digital string is all the ones and zeros. I needed to turn it into that. So what I had to do was make sure I could do an analog to digital conversion. And I was able to take my original signal, convert it to digital, and then go back to analog, which you see here. And actually, you'll notice it's a little bit fuzzy because you never get perfect resolution. So, problem number 1 solved. Next, I had to modulate this. So I used a modulation scheme known as phase shift keying. I actually used quadrature phase shift keying, which means I used 4 different phases. So that means that I can put 2 bits into each phase. What that means is, if you look at this signal down here, right, it looks like a sine wave. And when you receive this, you can read your phases, and the change in phase that you see in the breaks here tells you I have change in bits. So for up here, that change in phase tells me that's a 1. This one says it's a 0, 1, 0, 0. Down here, because I'm using quadrature, that means that I can actually have 2 bits per phase. Yeah. So then what I needed to do is, once I modulated it, I needed to simulate a multipath fading channel. So theoretically, this should look like this, and this comes from Nakagami's equation, and this is actually for m equals 1. So a Rayleigh fading channel looks like this, right? And I simulated that, and this is what I have. Looks pretty identical to me. Then I had to do Gaussian. Again, this is for m equals 0.5. Just put that into his original equation. And that's what it should look like theoretically. Here's what I have. So now I have my Rayleigh, I have my Gaussian, I have my modulated signal. If I put all these things together and then demodulate that, because now I should have my original signal with all the noise, now I need to demodulate it, I get something like that looks like this. So what you have here, on the bottom we have a signal to noise ratio. As I increase the strength of my signal as opposed to my noise, so my noise gets smaller and smaller and my signal gets bigger and bigger, the bit error rate, so the difference in the 1s and 0s, goes down. So I'll have much more exact signal as my signal noise ratio goes up. Right here I did this for a randomly generated signal, so I just made a bunch of 1s and 0s and made sure that it looked right. Also, you'll notice here, this blue line is the theoretical Rayleigh, so it should follow basically that, and this is what I simulated. It just follows that blue line very closely. This is for I used an audio signal, and I converted it into a digital string. And again, it did exactly the same thing, which is what I needed it to do. I needed it to follow exactly what a random string would do. Then what I did is I said, okay, as we increase the signal to noise ratio, we need to see that our phase separates out. So I said we had a quadrature, so I need 4 separate phases. When our signal to noise ratio is 1, you have this blob. And you can't do anything with that. You can't read that. That's horrible. At 25, you still can't really see anything. Maybe a little bit better, not really. At 39, they're starting to separate. And at 50, you can clearly see all of them. So at a signal noise ratio of 50, we should get a pretty clean signal. This right here is just another way of looking at that past curve that we had. So basically, as I increase my signal noise ratio, the number of errors in the signal I get drops. So you see here around 30, I'm getting 30 signal noise ratio. I'm getting close to 0 errors. Although you do have to remember that's times 10 to the 4th, so it's probably still a few hundred in there. So I started with my original signal, and I distorted it. And this is a signal noise ratio of 5. It's not very nice. This is what it sounds like. If you're talking on the phone and that's what you get, you're not going to be very happy. Signal noise ratio of 25. And actually, these are unrealistic signal noise ratios. 25, you're never going to get that. You can't get that with a cell phone. You're going to too high. You're going to get something down closer to 5 or 1. But this is 25 right here.
This is a test recording. It will not be very long.
I made that like when I was in applied programming, learning how to use MATLAB. And I had a project I needed an audio file. I made that, and I've just used it in every project since. Finally, we have 50. So you see here, almost all of our errors are gone, just like we expected. We still have a few errors in here, and if you listen to this, I don't even know if you'll really be able to hear them.
This is a test recording.
You can hear the little fuzzies.
It will not be very long.
Also notice that every time I played that, my voice got louder. So in the first two, the noise was really loud and the signal was so distorted that my voice was like a little mouse. But at signal noise ratio 50, my voice is kind of back to what it should be. So what have we shown here? Obviously, multipath distortion just kills radio frequency transmissions. But thankfully, they're actually not bad enough, typically, that we have to worry about them in commercial endeavors. So like with your cell phone, typically you can talk everywhere, even though this problem hasn't been completely mitigated. You can talk anywhere you have signal. And the reason for that is that you don't get multipath distortion everywhere. Unfortunately, for military applications, it has a very large effect. If we're using like a radar and we send the signal out, it can come back and tell us that there are 5 objects out somewhere when there are actually 1, or we won't actually be able to tell what it is. So that causes large problems for us there. But by increasing our signal to noise ratio, we can decrease the number of errors that we get. And even though that's not a practical solution, it is still a method of reduction. I'd like to thank Dr. Cornley. He's been an amazing help. He's very good with MATLAB and also probably one of the world's leading experts on this problem. And I'd also like to thank Nakagami for his painstaking work that he did back in the 1940s, pre-computers and digital cameras and whatnot, in developing the M-type distribution that I could use here. And that's it. Any questions?
Question for Dan.
And what was the signal to noise ratio on the first recording?
5. A little bit, but not really. It's usually less than that when you actually have multipath interference.
More questions for Dan?
Did you what you actually said was instead of multipath, a phase shift?
Yes.
Okay, so
Multipath causes a phase shift in your signal.
there might be other things, I guess.
Okay, so multipath, what happens, you have several signals. Let's say we're in this room, right? One signal goes out and bounces off that wall and heads back to John, right? And the other one hits that wall and comes back. Well, those two walls actually cause other types of interference. Your signal amplitude will change. You'll get different types of noise on there based on what they hit. And then also, they're traveling by different paths, so they take different amount of times to reach the receiver, right? So when that happens, the phase shift, that's where you get the phase shift from, is that they take different amount of times because they're traveling different length paths. So you get not only all the noise from hitting the wall or bouncing off the ionosphere like we do with radio transmissions, but you also get that phase shift. And what that phase shift does is you don't get anything like your original signal. You'll get some, very crazy looking wave. And if you look at that in the frequency domain, there's no way you can tell what's going on or separate out the original signal. Especially when you're using phase shift keying, because all your information is stored in the phase. So any phase shift will destroy your signal.
Now, have you ever plugged your phone or an amplifier or like a speaker set, and like you get like, you know, when you get a text, you get like a weird kind of sound in the speaker. Is that because of the radio frequencies as well, or is it just because of the signal frequencies, or?
When you get a text,
Yeah, and like it makes that weird noise and like.
I didn't understand. Ask the question.
Like you get a text and like you have like your like phone or whatever plugged in the speakers.
Oh, okay, that's echo. That's a different problem. That's called echo.
Uh,
It's an echo signal. It's the same signal coming back again. It's almost the same kind of thing with the phase difference, and it gives you an echo. Yeah. That's it? We good? That was an excellent presentation. So next week, one more. So come back next week to see the rest of the presentations. Thank you very much for supporting the John. All of you know John Newfree, right? That's his seminar.